Hello everybody! I will present you the paper Display-List a Distribution Adaptive Skip List. My name is Vitaly Aksionov and this work is done jointly with Dan Alistar from IST Austria, Alexander Dresdov from ITMO University and Amir Kivan Mohtashami from EPFL. So what is our goal? Our goal is to create a concurrent data structures that answers many concurrent requests of three types: contains, insert and delete. Typically, such data structures are tested under uniform workload, where each element is requested with uniform probability. Unfortunately, in real life, most distributions are skewed, and some elements are requested more frequently than others. Please note that most of the state-of-the-art concurrent data structures do not adapt to the distribution. Why I think it is not very good? If you adapt the data structure to the distribution, you can get statically optimal data structure, which has better complexity on the operation instead of O of logarithm m. To be more precise, it becomes O of logarithm m over pi, where m is the total number of requests, and pi is the total number of requests per element I. There exists a lot of statically optimal sequential data structures, such as, for example, based on the trees, play tree, tanga tree, and etc., and, for example, based on skip lists, for example, SACL. What about concurrent data structures? There exists only one statically optimal concurrent data structures, which is CB3. Unfortunately, CB3 has a few shortcomings. One of them is that during the contain separation, it uses hand-over-hand validation, which reduces the performance of the contains itself. Why it is important to have it in tree? Because CB3 uses rotations. And when you traverse the tree, you have to know that you come to the right branch, rather than the rotation can change it. So we think that we can build our data structure atop a skip list, because in the skip list, if you skip your branch, you still get to the lower level and you can find your element by getting to the right, probably a little bit longer than usually, but still we can find an element. Unfortunately, SACL data structure is not very easy to make concurrent, so we have to come with an alternative. And we create a Splay-List. So here is an overview of my talk. At first, I will talk about sequential Splay-List. Then I will talk about how to relax the sequential Splay-List and how to improve its performance. Then I will take how to make this Splay-List concurrent, and finally I will talk about the results of the evaluation. So how to make Splay-List out of the skip list? At first, we store per each node a number of requests, which we name hits. So then each operation performs like in a skip list. It traverses their Splay-List in the usual manner. So suppose we are looking for you and we are coming by this red line. And when we reach an element, we increase its number of hits. Then on the path backward, on the same path as we come forward, we check two balancing conditions: the descent condition and the ascent condition. What is the descent condition? The descent condition checks two neighbors on a level and check whether the number of requests to their subtrees is small or not. So what is the subtree in the skip list or in this playlist? So consider V. CVH is a subtree of V on level H. Is there elements that belong to this rectangle, or to be more formally, which are between V and U, but on the first level? So everything in this rectangle. With U the same, CUH is a subtree of U at level H, which contains all the elements that belongs to the first level between U and its neighbor. So if the total number of requests to this subtree is less than or equal than the total number of hits divided by 2 in a power that depends on the age, then we don't need to have two shortcuts on this level. So it will be enough to have V, but by reducing U, we can improve the performance of the other operations that are coming through this level. So it is a good idea, if the total number of requests here is small, then we simply demote U to the lower level. Then we also check the ascent condition. So we take U and count the number of requests that passed through this element on height H. So to be more precise, this is the number of requests per elements that are lying in this rectangle. Or to be more precise, to all the elements that comes on the first level between you and the next node with height higher than you. So we check if the number of hits there is high, or to be more precise, the total number of hits divided by 2 in the power that depends on the height, then we should promote you higher to help all the requests coming to this rectangle to make it faster. So we simply promote you to the next level. So consider this cat. This cat checks ascent condition and descent condition, and it finds that it has small number of hits. Then it has to get down. So here is an example. The total number of hits or requests is 10, and the height of this playlist is logarithm m, which is equal to 3. Please note that the height of this playlist depends on the number of requests, because by the descent condition we could demote the node lower than this playlist is. Thus we have to create another layer in this playlist. What is the subtree in the playlist? So C31 is a subtree of the node 3 on level 1. So we take all the nodes that are between 3 and its neighbor on level 1, 5. So this is 3, 4, 5. For the second node, its neighbor is 3 on the first level, then C to 1 is 2. Analogously, C of head 1 is head and 1, and for C head and level 2 should contain all the elements that lie between head and its neighbor on level 2, which is 6. So all head 1, 2, 3, 4, 5 belong to C head 2. What are the numbers there? The numbers on the lowest level are the number of requests per an element. So for example, here for 3, the total number of requests is 1. And for 6, the total number of requests is 5. On their higher levels, we maintain the total number of requests to the subtree except for the request for the node itself. So for example, for 3, we have in the subtree is 3, 4, 5. In total, we have the total number of requests as 3, and minus the number of requests per 3, so it is 2. For second node, for example, there is no other nodes between 2 and 3, thus it has 0 here. So suppose that we start a request contains 5. We go by the red line to reach 5, and we should increase the number of hits there. So we get our magic cat who changes our data structure. So whoosh, and we have 2 instead of 1 at the place of 5. Then we go backwards by the backward path and check ascent and descent conditions. So we take it first for descent condition, the total number of hits per the subtree of 4, a subtree of 3. So it is 1 plus 1, in total it is 2, and we compare with 11 over 8. So it doesn't satisfy the descent condition. What about the ascent condition? We should take 4. We should take the next neighbor on higher level, so it is 6. So we have 4, 5 as the suffix for 4. And in total we have 3 requests here. So 1 in 4 and 2 in 5. So in total we have 3, and you compare it with 11 over 4. You find that 4 satisfy the ascent condition, and we should increase its height. At the same time, the total number of requests to the subtree by 3 should also change. So we take our magic cat and it changes our data structure. So here it becomes 2, and on the 3 it becomes 0 because 4 now is the neighbor of 3 at the level 1. Then we go in backwards on the path. So we take 2 and 3 and check for the descent condition. We see that the descent condition, we should count the number of requests per the subtree of 2 and the subtree of 3. In total it has 2, and we compare it with 11 over 4. Thus it satisfies the descent condition, and we should decrease the level of the element 3. Then we should change the counters of 2 and head. So let the cat does everything. Okay, we change everything, and that's how we change the data structure in this example. So how contains insert and delete typically work? So in contains, we traverse the data structure, then we increase the number of hits per this element, then we traverse back, change the counters, and apply all the conditions. In the insert, we traverse the data structure, and then there are two conditions. If there is no such element, then we insert it at the lowest level with one hit. Or we can find an element that is marked as deleted. Please note that our deletion is typically logical, so we simply mark it as deleted or not. So we unmark as deleted, we increase the hits, we traverse back, we change the counters, and apply the conditions on the way back. For delete, we traverse to the element, mark it as deleted, increase the number of hits per it, traverse back, change the counters, and apply conditions. And finally, if the number of hits per logically deleted nodes is high, then we should improve our data structure and rebuild it. Please note that it is a very good thing to have because it improves the performance, and at the same time, since the number of hits per logically deleted nodes is, for example, half of the total number of requests, we can amortize the whole rebuild to this logically deleted nodes. So here is an analysis. At first, we prove that after any operation, no node can satisfy the ascent condition. Then, if we look for the element u, we start the path there, like the red path, and we come to an element. The number of visited levels until we find an element is of logarithm m over hits of u, where m is the total number of requests and hits of u is the total number of hits per u. Then the next lemma is that we visit at most 4 nodes per level that do not satisfy the descent condition and thus that are not descended. So suppose that we have 5 nodes. So we have u1, u2, u3, u4, and u5. So u3 and its neighbor has a lot of requests because it doesn't satisfy the descent condition. And for u5 and its neighbor, there are lots of requests then because u5 does not satisfy the descent condition. Thus, their element u2 has a lot of requests in its suffix or in this rectangle. Thus, we could ascend u2, but we already proved lemma 1 that no node can satisfy the ascent condition after an operation. Thus, we get a contradiction and we have at most 4 nodes per level that do not satisfy the descent condition. Then the theorem 1 becomes very simple. The operation that hits u costs logarithm m over hits u, which are per the elements that do not satisfy the descent conditions, because this is 4 times the total number of visited levels, plus d, where d is the number of occurred descents. Then, please note that when we insert an element, we insert it on the lowest level. So it has kind of only one ascent. Thus, the total number of descent that is done in the data structure, it cannot increase the total number of ascents that are done. Thus, we can see that the total number of ascents can be at most the number of visited levels. The operation that hits u takes off logarithm m over hits of u, amortized time. All other operation takes off logarithm m. So here comes the rebalancing idea. It's pretty obvious that two-way passing has very extra cost. So we kind of want to improve the performance. How to improve it? Let's rebalance periodically. So sometimes we just traverse to an element and do nothing. And with the probability 1 over c, we go backwards and rebalance the tree. And we prove the following theorem, that if we perform rebalancing with probability 1 over c, the operation that hits u takes off c times logarithm m over hits of u. So if c is constant, then the complexity doesn't change. Please note that we cannot prove the same bound for CB3, so it has stronger guarantees. Here is you, the relaxed cat, as our relaxed data structure. So what about concurrent implementation? At first, the first issue that comes to mind is that we rebalance forward and backwards. And when we rebalance backwards, we should take locks on all the nodes in the path, which is not very good. So what is our solution? At first, as we already told, we rebalance backwards only with probability 1 over c. However, we will now make the rebalancing operation not backwards, but forward. Let's look at the picture that we had previously and consider which element can satisfy the ascent condition. Please note that the hits or the number of requests per their suffix rectangle can increase only by 1. Thus, the first node that can satisfy the ascent condition is only the first node on that level with this height. So, only one node per level can satisfy the ascent condition, and it is only first node. So, our rebalancing then will work forward. We will lock the topmost node and the rightmost node on the level by the path. And then we check whether the first node on the level should be ascended. Then we release the topmost node and lock the node on the third level, the rightmost by the path. And then we check for ascent the node on the third level, and so on until we get to the node. So by that we have forward hand-over-hand locking, which is much better than locking everything on the backwards path. What about list expansion? We told that if there are lots of requests, we have to increase the height of the Splay-List. We increase it lazily. We allocate 64 layers per each node and maintain the lowest level of each node, and we maintain the lowest level of the whole Splay-List. And then we get to the node and we see that the lowest level on the whole data structure is lower than the lowest level of our node. We simply update to the current level. How to implement the delete? We do a logical deletion as we talked before, and when we need to rebuild the data structure, we just take a huge lock on whole data structure. So let's come to the experiment. So we have a setup where we have 4 sockets Z on gold with 18 threads per socket, so in total 72 threads, and we test on 8 workloads. At first we have uniform workload where we ask contains operations on 10 to the power of 5 elements with uniform probability. Then the next workload also on contains requests, and it means that for 10 in the power of 5 elements, 90% of requests are for 10% of elements, so it's kind of skewed. Then this workload is 95% of requests for 5% of element, and finally the most skewed that we choose here is 99% of requests are for 1% of elements. And finally we will talk the zip1 workload, which is kind of the distribution of the frequency of English words. Also over 10 in the power of 5 elements, and also only contains operations. So we have 2 questions. The first question, is the sequential Splay-List faster than skip-list on the CB3? We want it to be faster than skip-list on skewed workloads, and it should have shorter paths to their target. And we want to check whether it is faster than the CB3. We expect that CB3 should be on 1 thread faster because it is more compact. In Splay-List we have each node of size 64, which is very high. What about the second question? Is the concurrent Splay-List faster than the skip-list and the CB3? We want it to be faster than skip-list and CB3 on skewed workloads, and it should be slower by not much on uniform workload. So at first, We will start with our power supply cat, who generates us an electricity, and then we come to the sequential execution. So in our experiments, we chose different update rates, and we choose the best one for this playlist and for CB3, and it is 100. So we update only once in 100 of operations. So consider the first workload where we have 90% of operations per 10% of keys. And other two workloads which become more skewed and more skewed. So at first, this playlist is faster than skiplist by 1.12, and on the most skewed one, it is faster by 2.01, which is quite high. Please note that their average path was shorter for 9010 in 1.3x, and on more skewed, it is 1.67. Please note that their improvement is increased by their skewedness of the distribution. Unfortunately, Splay-List is not faster than the CB3, but the more skewed their distribution, the better we perform in compared to the CB3. So at first we had approximately 1.6 times, and finally we have approximately 1.10. Sorry, 1.20. So what about concurrent execution? So we run on the uniform, and we can see that we use 4 algorithms. So we have Splay-List, Skip-List, and we have 2 versions of CB3. The one that is presented in the original paper, CB3 Unfair, is that there is only one thread that rebalances the tree. And red one is CB3 Fair, where all nodes are rebalanced by all the processors. So you can see that on update rate 10, where we have once in a 10, we see that Skip-List outperforms Splay-List, which outperforms CB3. Then on update rate 100, we have Skip-List outperforms CB3 and Splay-List, and the same happens on update rate 1000. Please note that on the x-axis we have number of processes, and on the y-axis we have the total number of operations per second. So the more skewed their distribution is, the better our Splay tree performs in compared to Skip-List. So we are getting better, and at the same time we improve in comparison to CB3. When it becomes more skewed and more skewed, so on 95.5 we already outperform Skip-List, and on 99.1 it outperforms Skip-List by much, and CB3 outperforms Skip-List also. Finally, we will talk about zip1 workload, and here we see that Splay-List outperforms all other data structures, which is very good. So for the conclusion, we choose out of the previous results the best trade. It is again becomes 100 for Splay-List and CB3. On this table, you can see the relative number of operations per Splay-List. So for example, Skip-List has 2 times more operations, and CB3 has 1 divided by 0.77x number of operations. So if we have less than 1 here, then Splay-List performs worse. But as you can see, there are only 3 boxes of red, and all other boxes are green. So it means that we outperform the Skip-List and CB3. Please note that on the more skewed workload that we have, we outperform Skip-List by a lot, while we outperform CB3 a little bit less, but still much. So there is a reason for our Splay-List data structure, at least on the skewed workloads. So we came to the most yummy part, takeaway. So we presented the self-adjusting Skip-List with simple ascent-descent conditions. We showed it relaxed version with the guarantees, which is very important in comparison to CB3. We showed how to make concurrent log-based implementation, and finally we showed that it is faster on skewed workloads and on high number of processes in comparison to Skiplist and CB3. Thank you very much for your attention.